Okay, this is a video for MAC1105 section 3.5, numbers 1 through 5. In this section, we're going to be looking at rational functions, and a rational function is any function that is in its numerator, has one function written in terms of x, and then in the denominator, a different function written in terms of x. And when you are graphing these functions, you're going to see that a big part of graphing them is being able to tell where the areas of discontinuity are. Like for instance, if you look at this graph down here towards the bottom of the page, notice that there's an area where the graph is broken. That's called an area of discontinuity. What you're seeing here is a vertical asymptote, which is the y-axis. Or you could also call that the line x equal to 0. But right here you could actually draw the vertical asymptote in. When you look at it on your graphing calculator, it's only going to show an area where the graph is broken, but when people graph it by hand, they typically draw in the vertical asymptote. So you being able to find these areas of discontinuity, vertical asymptotes, and then we'll also talk about horizontal asymptotes, have to do with you first understanding the domain. When we do start looking for vertical asymptotes, it'll have to do with the denominator, and sometimes it will also involve the numerator, because there's going to be a point in these problems where you have to decide, am I looking at a vertical asymptote or am I looking at what's called a hole? So by the time we get to that, I'll make a point as to how you figure that out. But for right now, let's just start with a discussion about the domain. If you remember this from chapter 2, the domain, when you're looking at any kind of a rational expression, rational means fraction, you're looking at the denominator, because this being 0 is what makes this whole fraction undefined. And you never want to cancel anything before you're looking for the domain. You want to state what the domain is in its unsimplified form. When we go to look for vertical asymptotes, which I'm going to be calling VA as we go through this discussion, we're going to have to look at more than just the denominator in order to tell, like I said, whether it's a vertical asymptote or whether it's a hole. But for purposes of the domain, which is what the question is right here in number 1, look at these problems in their unsimplified form. Do not cancel anything. So what would make the denominator 0 is the value 3. So x may not be equal to 3. So when you state what the domain is, here's the symbolic way to write it out. You can write x can be any element of, this symbol right here means element or member of, the real number set. Then typically there would be a comma, and then you state what it can't be. Those are called the exceptions. This is if you're going to give it in set notation. If you want to write that out in sentence form, you could write it like this. I'll write it up here since there's not much room. You could write x is, this is how you write it in words, any element of the real number system, but x cannot be 3. And basically, this is just how you verbalize what you just wrote here. That's why people like to write it like this. So you'll have to see what MyMathLab offers you as far as options for answering. But they'll make it easy enough for you to say it. So this is in symbolic form. This is in word form. Okay, for this one. Now, when you're doing these, it is okay to factor, because factoring reveals what all the numbers are that it can't be on the denominator. I just don't want you to cancel when you're factoring. So just to reiterate, it's okay to factor. In fact, you're going to probably have to do that here. Just don't cancel with anything and then start saying what the domain is after you've canceled things. This is the difference of squares. factors like that. The number that would make, let me remove this word here. I'm just going to erase that. I have some more room to finish answering this question. Okay, so the number that would make this factor equal to 0 and therefore make the whole fraction undefined would be the value 3. So x can't be 3. And then the number that it can't be right here would be x equal to negative 3. So it can't be 3 and it can't be negative 3. So if you were going to state this domain in symbolic form, and then you can always write it in words because this is just how you verbalize what you're writing here. In symbolic form, it would be x can be any member or any element of the real number set, except it can't be 3 and it can't be negative 3. Okay, so in that case, there was two different values. Part C, there's no way to factor x squared plus 9. You can only factor x squared minus a number. Then you can use differences square as your factoring method. But when there's a plus sign, it actually can't be factored. And therefore, there's absolutely nothing that's going to destroy this denominator and therefore make the fraction undefined. Because if you put positive 3 in here, it's 9 plus 9. You haven't created a 0. Where if you put a negative 3 in here, it's negative 3 times negative 3, which is also 9, and that can't hurt it either. And those are the only two potential values that were going to hurt this kind of expression, which you were probably thinking of because the way you factored over here. But because of the plus sign, the domain here is all real numbers, which you can write like this, or you can write out x is all real numbers for the domain. Okay, so there's the answer for that. This is the answer for B. This is the answer for A. Okay, so as I was talking about these graphs and pointing earlier in the discussion to the fact that there's discontinuity, this is what we call the parent graph when you're talking about rational expressions. When you have an x to the first degree in the bottom and a constant on the top. You have what's called these two hyperbolic wings. The only number that could make this denominator 0 is the actual number x equal to 0. That would cause this whole thing to be undefined. So the value that makes this undefined, in other words, what makes the denominator 0, that's where you're going to see this area of discontinuity. When you're drawing it by hand, you're probably going to darken in that what's called the vertical asymptote. It's just a vertical line that separates the graph into two pieces. Some of these graphs have 3 areas that you're going to graph in, and you can always, use your calculator to help you with those shapes. This is what we call the parent graph. Now you're going to see them start talking about how certain values of the function are approaching infinity. So you have to know how to speak in that language. So when you're looking at this comment down on the bottom, what this says is the arrow means approaches. If you want to write that word in. And you have to know what side you're approaching from. As x approaches 0 from the left side, the negative side is the left side. Like if you're thinking of a number line here, the negatives are on the left, the positives are on the right. So as you approach, as your x values approach 0 coming from the left. So as your x values approach 0 coming from the left, what this is asking you right here is, what is the actual function doing? In other words, the graph. I mean, they're also talking about the y values here, so you can read it like that. As your x values approach 0 from the left, here we come from the left, we're approaching the x value called 0. What is this graph doing? It is shooting down to negative infinity. You're not talking about this side because it said approach it from the left. If you were coming this way, you'd be approaching the x values would be approaching 0, but you're coming from the right side. So you have to read this comment here, whether there's a negative or a positive. And when they talk about f of x, they're talking about what is the graph doing? What are the y values on the graph doing? See, those y values are going down to negative infinity. So that's where they have that. And they're going to ask you to complete questions like this on MyMathLab. Like potentially they would just leave this open and you would have to tell them what's going on with that. Okay, just giving you a rundown of how to, answer some of these questions. We'll get to the problems eventually. Okay, so now this says, as x approaches 0 from the right, let's look at that graph again. As x approaches 0 from the right, I kind of already pointed that out to you. But if you were on this same graph and you were being asked that question, as x approaches 0, but from the right side, what is f of x doing? In other words, what is the graph doing? And probably they would just leave this blank on MyMathLab and you would go and fill it in. So if you're on the right side of the y-axis and the zeros are getting, the x's are getting closer and closer to 0. X is approaching 0, but coming from the right. What is the graph doing? That graph, or the y values on the graph, are going up to positive infinity. And that's what you would fill this in. And then I think there's another problem like that on the next page. As x approaches infinity. So let's see, as x approaches positive infinity, and then it has what is f of x doing at that point? Okay, so let's let x approach positive infinity. That only can mean that you're on the right side, because this is where positive infinity is. You know that when they don't put a plus there, which I don't think they did, then that automatically means that it is positive. Okay, so if your x values are getting close, or if your x values are moving further and further aligned, getting bigger and bigger and bigger, that's what it means for x to go to infinity. Do you notice that this graph is getting close as you move out this way? That the graph is getting closer and closer and closer to the x-axis. Well, the x-axis is also called the x equal to the y equal to 0 line. Okay, and you are talking, f of x does mean what are the y's doing. So another name for the x-axis is every single point on the x-axis has a y coordinate of 0. That's why we call this line, sorry about that. Try to make that not happen again. Yeah, it's hard not to have noises here. You have the phone going off, the dog's over here snoring. Oh well. Okay, so as x approaches infinity, your y values are getting closer and closer to the x-axis, which again is called the y equal to 0 line. So this would be 0 because they are asking you to fill in what's happening to the function, which is really the y values. Okay, so that is what this and this was about, and there's just more of this notation here. And I recapped all of it here as well, but that was 3 examples having to do with the type of questions that they can ask you. Okay, as you get to the problems here, I guess I was counting all of that, page 1 and 2. Okay, so we did number 1 on page 1. And now we're on page 2. So now the question is, rather than what is the domain, now the question is, what is the vertical asymptotes? And you have to be careful when the question changes to this rather than the domain. You have to be careful about also looking at the numerator, because sometimes what you are getting ready to call a vertical asymptote is really a hole. So we want to be careful with that. That's what this is about. If your function is a rational function in which p and x have no common factors, then x equal to a is a vertical asymptote. So what they're saying is this: you have to make sure, and B will be a very good example for me to point out the difference between a vertical asymptote and a hole. I can basically break it down like this. If you go to factor that bottom and there's anything here that cancels with an expression in the top, then that thing's going to be called a hole rather than a vertical asymptote. When I get to this one, I'll write that out for you. Okay, now you want to be able to tell what makes the denominator 0. It's the first question you're asking yourself, as though you were answering what the domain is. What makes the denominator equal to 0? Okay, so to do that, you have to factor, just like we did in a previous problem. This is x minus 3, x plus 3. Okay, so the things that would make the denominator equal to 0 is positive 3, so x can't be 3. And what would make this 0 out, this particular factor, would be negative 3, so x is not allowed to be equal to that. So when they say, what are the vertical asymptotes? These are the things that it can't be if you were being asked, what is the domain? Okay, these are the questions that we just asked on the previous page. When you switch over to this kind of question, what is the vertical asymptotes? Then you talk about these values in their positive sense, as though there was a line dropping right through those numbers, as though there was a gap of space, like an area of discontinuity. So when you switch over to this being in the sentence where you're asked the question rather than the word domain, then instead of saying x can't be 3, you say at the line called 3, there is a vertical asymptote. And here's the picture right here. See, there's a vertical asymptote. If you're not doing it on a calculator, you're going to draw it in. So here's a line right here, and there is discontinuity there. In other words, part of the graph is on one side of the vertical asymptote, and then the next portion of the graph is on the other side of this line right here called x equal to 3. So that is your first vertical asymptote at x equal to 3. It's just that when we name vertical lines, it's always x is equal to and the number that it goes through, which is 3 in this case. Okay, then the other vertical asymptote is the number that made this, that would create a 0 right here in this factor. So because you're not talking about domain where you talk about what it can't be, you talk about it without the little not equal to slash sign. So this would be the other vertical asymptote, as you can also see that one in this diagram. See right here at this number, you can see that there is another gap in the graph. In other words, there's a portion to the right of this second vertical asymptote. It doesn't matter which one you do first. And there's a portion of the graph to the left of it. Okay, but again, when you're talking about domain, you say that it can't be those values. When you're talking about vertical asymptotes, you talk about the values as though, that they're vertical lines. Okay. All right, let's see. And that's all you're asked. You haven't been asked to actually do the graph yourself yet, but that will come. When you get to part B, this will be a good chance for me to explain the difference between a hole versus a vertical asymptote. Okay, this versus this. So when you go to factor this, just as you have factored this is the third time we're factoring this same expression, x minus 3, x plus 3. Do you see that this time when you go to factor it, as opposed to part A, that the x plus 3 cancels with the x plus 3? That didn't happen over here. There was no expression that canceled with anything in the top. So when you have factors, try and write this out, factors in the denominator and numerator that cancel. That's when the value of discontinuity represents a hole. When it doesn't cancel with anything, like this x minus 3 doesn't cancel with anything up here. So this one will be called a vertical asymptote at the value that makes it 0. So your vertical asymptote is at what makes this 0? This would be x equal to 3. Whereas the thing that makes this 0, which is x equal to negative 3, that one represents a hole. Again, because it is a factor that cancels with something in the numerator. Okay, so that's the difference between that and a hole. And you can see that in the graph right here. See, right at x equal to negative 3, instead of dropping a vertical asymptote, they continued with the graph and just put, they continue with the graph, and then you can just go and erase the part and draw a hole at the x value that the hole exists. But here, there is a true vertical asymptote. Okay, so that's the difference. There's your hole, there's your vertical asymptote. Okay, moving on. These are just the equations that go with these. Number 3. Okay, now let's see, where did this graph come from? Okay, so I believe, even though they wrote it again, this was the function that was mentioned right here, but then they stated it again right here anyway. So we're talking about the graph. Now, why does the graph have no vertical asymptotes, no holes? And that would be because this denominator that you see right down here, x squared plus 9, you can't factor it. And the only way that you would have vertical asymptotes is if you could factor it and could then find the values that make those factors equal to 0. But since you can't factor the denominator, there are no vertical asymptotes. And because you can't factor the denominator, there's no holes because there's nothing here to cancel with the top. So because there's no vertical asymptotes and no holes, those are called areas of discontinuity. They break up the graph. That is why you have a nice, smooth, continuous graph here. No areas where the graph is broken. Okay, number 4. Okay, here you have the function showing any vertical asymptotes or holes that exist. I believe this was supposed to say graph the function. Please add that word in there. Okay, so let's do it from start to finish. Okay, so basically you're looking right here. You cannot factor this. So you want to ask yourself, is there a vertical asymptote or is it a hole as you consider what's going on in the denominator? Now, does this cancel with something here? Yes, it does, because when you go to factor the top factors like this, and I was going to call this a vertical asymptote, but then I noticed that what's in the bottom here cancels with one of the factors that's in the top. So the only thing that's left on the top is x plus 2. And instead of this being called a vertical asymptote, we're going to call it a hole. So that there is a hole at x equal to, now go and look at the value, look at these things that you just canceled. Okay, because you have factors that cancel. That means that at x equal to the number that would make either one of these 0 is x equal to 2. So factors that cancel, x equal to 2, means that you have found a hole. All right, so the remaining part of the graph, you can find, the shape of the graph, you can find it by your calculator. But basically, I could tell you what it is. You can also do this by hand. After these canceled, all we had left was this. And we'll put it in the calculator as well just to verify what the picture looks like. But this is y is equal to mx plus b. Anytime you have first degree equation in your x and y, this represents the slope, this represents the y-intercept. So this is your y-intercept. And you can put the whole in afterwards if you want, or you can put it in right when you are right while you're graphing it. So the y-intercept is 2, and then the slope is 1 over 1. It has to do with this coefficient of x. So rise over run if you want to do this by hand. And if you were going to put it in the calculator, you could just put in the x plus 2. No, you could put in the whole thing also. Let's see, but if you do put in the whole thing, you're going to have to wrap a parenthesis around that as well as a parenthesis around the bottom. And I wouldn't put it in its factored form because that's going to even be more of a hassle. So the easiest way is just to put in what remains, if you are going to put it in your calculator, what remains after you cancel. F of x equal to x plus 2. So anyway, if you're going to get the rest of this graph by hand, after you plot the y-intercept of 2, it would be rise 1, run 1. Rise 1, run 1. Rise 1, run 1. Run 1. So just at 2, don't forget there's a hole. See, that's the x value called 2, which I got by rising 1 and running 1. So when you graph it, like that. And when you do the rise and run, instead of rising 1 and running 1, you could also rise down 1, run 1 to the left. Like do everything with the opposite sign, the rise and the run. Down 1, left 1. And you can get the whole graph like that. Okay, so there you go. That's your hole. Don't forget the value that zeroes out the denominator is a vertical asymptote unless it cancels with something with a factor in the numerator. Okay, moving to number 5. Okay, so in number 5, we want to start working on how do you find the horizontal asymptote? Because as you can see, like look at some of these graphs here in problem number 6. Do you see how there is also part of the graph is way up in the air and part of it's below? And that's because there's a horizontal asymptote, if you kind of look at that real closely, right at 4. So you have part of the graph above it and part of the graph below it. Not only that, you also have a vertical asymptote. So we've already talked quite a bit about how to find a vertical asymptote, and now we're going to find out how do you find that horizontal asymptote if one even exists. Okay, so all of this, I don't know, it might be a little bit hard for you to understand, but what you should zero in on is this information right here. They're calling n the highest power in the numerator. That's also known as the degree. Because the degree of a polynomial always refers to what's the highest degree. So this n value is the degree of the numerator. And the m value that they're talking about is the degree of the denominator. I think you should get used to always comparing the top degree to the bottom degree, because if you're doing it in the reverse sometimes and looking at the top and then the bottom in other cases, you're going to get them mixed up. So always start by looking at the degree of the top and then comparing it to the degree of the bottom. So we got a degree in the denominator of 2, a degree in the top of 1. So what this says is, okay, that n that they're referring to is 1. That's the degree of the top. The m that they're calling it by, the degree in the bottom, is 2. Not that you need to write this out like this. You can just compare highest degree here to highest degree there. When the degree of the top is less than the degree of the bottom, this is what case 1 says right here. The horizontal asymptote of the graph is going to be the x-axis, also known as y equal to 0. So this is when the top is less than the bottom. Okay, so the asymptote in this particular case is You want to say the asymptotes like an equation. Y equal to 0 is the horizontal asymptote in part A. Okay, and that's because the degree of the top is less than the degree of the bottom. Okay, so this would be that case that you're seeing right here. Degree of the top less than the degree of the bottom. Okay, when you come to this case, notice that the degree of the top, which they have been calling N, is 2. And the degree of the bottom, which they have been calling M, is also 2. So when the degree of the top is equal to the degree of the bottom, not that you need to write that out or that out, because you can just glance at it and go right into your decision about where the horizontal asymptote is, but that means you need to memorize these 3 cases. Case 2 says when the degree of the top is equal to the degree of the bottom, then the line called y equal to a sub n over b sub m is the horizontal asymptote. Let me say that in an easier way. The horizontal asymptote in this case will be y is equal to, and all you're going to do in order to find the number that you had here automatically, because here it was automatic. When the top is less than the bottom, just y equal to 0. The x-axis is the horizontal asymptote. But here you have to come up with the number. So I know this is a little hard to understand. It's just the coefficients right here. See the coefficient of 4, coefficient of 2? You're going to create the number here by making a fraction out of those 2 coefficients. So y equal to 2 is your horizontal asymptote for part B. Okay, and part C. Now we're in case 3, because here the top degree is 3, which they've been calling M, and the bottom degree, which they've been calling M, is 2. So when the top is greater than the bottom degree, it is said that no horizontal asymptote exists. I mean, there is an asymptote, but it's called an oblique asymptote, and you guys are not responsible for that, but you will talk about it in pre-cal should you go that far. Okay, so that takes us all the way through problem number 5. Number 6 through the end of the section 3.5 is on the next video.